Hello, I'm Stephen Adams, and in this video I'd like to discuss the word logic. What does the word logic mean to you? For me, logic is a system of correct reasoning that is at the core of problem solving. We can do lots of critical thinking, but if our reasoning is flawed, then we end up off in left field. We're seeing a lot of this in society right now. You pick your favorite conspiracy theory, and you'll see a wonderful amount of thinking going on. But somewhere inside their logic, something's just not quite right. And when you address that central problem, the whole thing unravels. Now, how to pick apart the logic of an argument is the sort of thing you would do in a philosophy class or a debate club. You'd learn about things like straw man arguments or begging the question. But when we talk about confirming the logic of ideas in this course, what we're really talking about is starting with the given information in the form of a problem, create a process that uses the things we know to arrive at a solution that presents the correct answers. So let's dig into that right now. When we talk about logic, you'll often hear words like implication, inference, and deduction thrown around. An implication is a relationship between two ideas where if one is true, the other must be true. An inference starts with a conclusion and works backwards to say these are the facts that are required to make this conclusion true. And a deduction is reaching an answer through reasoning, a conclusion that must be true if all of these given facts are also true. Let's try a quick example to see if we can make this a little bit more clear, which may or may not have any resemblance to the real world. Let's start by defining a rule. We'd call this an axiom in formal logic. Now, our rule is going to be all cats have four legs. The thing about axioms is they are true without proof. If we discover at some point in the future that they are in fact not true, then our entire logical system falls apart. Everything that relies on that rule has to be double checked. This is why we have to be very careful when we make assumptions when we're reasoning. So, we have our rule, all cats have four legs. Now if I show you a cat, you can state the implication that since it's a cat, it has four legs. Even if you could only see the head and ears, you know it has four legs. Now, if I show you an animal, you could make the inference that it is a cat if it has four legs. That's the way our rule works. If I show you an animal with four legs, you might state the deduction that since it has four legs, it is a cat. Now, I said these don't bear any resemblance to the real world. What happens if I show you a dog with four legs? Can you deduce that my dog is a cat? No, you can't, of course. There's an important order here. I said all cats have four legs. I did not say that all animals with four legs are cats. And that is really important. You could make the inference that it might be a cat, but you can't come out and say conclusively if you know that there are more animals out there. If I added a fact that said all dogs have four legs, then definitely it would be clear that your inference has to say it's either a dog or a cat. Our deductions are only as good as the facts that we have, and that's one reason why it's really important to understand as much as possible about a problem before starting into the solution. In the example for the spy with the rust-colored coat and the dinner party guests, these puzzles really rely on using inferences and implications to try to riddle out all of the different facts that are available. We don't always use it so obviously. It's usually worked into the way we're thinking anyway, but as we go through this course, it'll be helpful for you if you can actually identify what information comes from what source. And that justifies whether or not your answers and your solutions are going to be correct. Just as we have a few different words for reasoning, we have different kinds of reasoning. We have, for example, deductive reasoning. You use deductions to combine premises and reach conclusions. I mentioned a minute ago the example that all cats have 4 legs. This animal is a cat, therefore the animal has 4 legs. That's your typical deductive reasoning. To put it in the usual language, this animal has 4 legs is our hypothesis or theory. As long as no premise contradicts our hypothesis, then we can use it to be true. New evidence might cause something we believe to become untrue. However, as long as those axioms and premises all hold, then we can be certain in our result. Inductive reasoning is sort of the opposite of deductive. This is our example of starting from the premises, this animal has 4 legs, cats have 4 legs, and making the conclusion that the animal is a cat. You've already seen a 4-legged dog is not a cat. However, it is possible with inductive reasoning for the premises to be perfectly true and to reach an incorrect conclusion. This is the kind of reasoning where we want to create hypotheses and we can say, if this is true, then this is the way we go. If this is true, then this is the way we go in reaching our decisions. Okay? The key here would be to word it as, this animal may be a cat. We haven't disqualified it from being a cat, but we need more facts to confirm it. Abductive reasoning is the kind of reasoning you use when you're faced with incomplete information. This can be thought of as circumstantial reasoning. You're trying to reach the most likely possible conclusion from the available information. This kind of thinking is very useful for creating theories and hypotheses, but it can turn out wrong. It can take you down the wrong tracks. For example, if I had a glass of milk on my table when I left the room, and when I returned I found the glass knocked over and the cat drinking the milk, it's possible that somebody looked in through the window, thought the cat looked thirsty, knocked over the glass for the cat, but it's far more likely that the cat knocked it over. But without more information, we really can't come to a firm conclusion on which one it was. All of these types of reasoning play different parts in software development. Many of the rules you are going to learn about how programming languages work follow deductive reasoning very, very strongly. The computer is excellent at matching rules. It's terrible at making a decision or a judgment call that it hasn't been programmed for. So, after a bit of practice, you can even start writing your own rules into the programs to reach conclusions. But the computer itself doesn't have that innate ability to think. So it has to follow deductive, strict rule matching almost all the time. Inductive reasoning is more likely to appear when you try to find an answer to a problem. You make some conclusion about how the parts of the problem fit together, and then you code them into the computer and check out to see if it works the way you expect it to. Both inductive and abductive reasoning play major parts in debugging your programming. Finding small errors that are introduced either from some way that you've coded it or from your logic, trying to fish out where those errors are and fix them requires a more creative approach to reasoning. A common source of errors in our reasoning on and off the computer is not recognizing the things we're relying on to be true. That is, do we check our assumptions and make sure they're correct? When you go to the store and pay for something by tapping your debit card, you're assuming a whole bunch of things. You assume you have enough money in the bank. You assume that the communication between the store and the bank is working. You assume the tap feature of your card is operating correctly, and on and on and on. And we don't usually think about those assumptions unless we're designing those systems, or if something has gone wrong and then we need to start troubleshooting. When we develop software, we want to try to account for as many problems as we can so that our program doesn't crash if the user of the software does something unexpected. If I ask you to enter a number into my program, is it safe to assume that you're going to do it? What else could you do? What happens if you do something unexpected? In the first half of the course, we're going to make some assumptions that make our lives a lot simpler. We're going to assume that the users put in the correct kinds of values, that they put in pretty reasonable values, all sorts of stuff like that. We're going to assume that the user is smart and that they won't do anything to break our program on purpose. In the second half of the course, we want to build more real-world software, and so we're going to assume that the user is either dumb or malicious. We're going to just try our best to keep our programs from crashing, no matter what the user does. In order for you to handle some of these situations, you have to first recognize that you made an assumption. Because if you don't know that you have an assumption in place, how can you be aware that you need to do something to back it up? Now, it turns out in the real world, a lot of times we do work under assumptions and we don't double check things. And that is perfectly okay as long as everybody is working under the same set of assumptions. It takes time to double check things, and when we start dealing with high efficiencies, we really don't want to spend that time. In order for you to demonstrate that you're aware of the assumptions you're making, we're going to get you to comment your code. It's perfectly okay to make an assumption, but we want you to state that you've made it. That way, we know that you know that there is an issue there that you might have to deal with later on. Reasoning out a solution to your problem is only the first step. As you saw from our conclusion that a dog is a cat, it's pretty easy to make a mistake and get the wrong answer. As a software developer, you need to test your programs and make sure that you get answers that make good sense. There's many logic puzzles available that can help you with building up your reasoning skills, especially the ones that rely on deduction and implication. The hardest puzzles require you to make inferences and to test out different ideas in search of the correct answer. The game Sudoku is excellent at bringing these three different logical skills together in different difficulty levels. In this video, we've talked about the importance of identifying the assumptions you're making and what is going to happen when you're assembling a solution to a problem. I defined implication, inference, deduction, and gave a quick example of each. You saw an example of an incorrect interpretation of logic and why we have to be very careful with inferences. You've heard about deductive, inductive, and abductive reasoning, and I tried to give you some idea where that all fits into developing software. Finally, we talked about documenting any assumptions that we are making and why that is important to our final solutions. The example puzzles in this unit will demonstrate to you why memorizing a solution will not help you succeed very much in this course. If a clue changes, the solution changes. If you're asked about why something is true, then the memorized solution will not give you that explanation. Working through the examples, challenging yourself outside of class is the only way to develop the skills that you need to succeed not only in this course, but in many others. Thanks for listening. Until next time, I'm Stephen Adams, and I'm hoping that you are having a great day. Bye for now.